And we are back. Welcome to this very special pre-summer bonus episode of Webinar Wednesday, hosted by the Concrete Preservation Alliance. I am your favorite, and yes, only moderator for this series. My name is Scott with Vector Corrosion Technologies. Yes, you've been calling for it, you've been demanding it, so we've put together a webinar today focused on an introduction to designing with galvanic anode systems. This likely will be the first of a number of design-focused webinars coming up, so we hope you enjoy today's program. Without further ado, we'll just get going here. For those of you who've joined us for our bridge preservation series or our parking structure preservation series, you know that the Concrete Preservation Alliance is a coalition of like-minded organizations that come together to share best practices in the field of concrete preservation and infrastructure renewal. We have a significant number of members across the globe, and we're thrilled they can be a part of this growing group. And if you've joined us here today, you've been to the WeSaveStructures.info website where you've registered for this webinar under the Events tab. We try to update this website frequently, so please return back for either new webinar registrations or the slide decks from past webinars or the recordings from past webinars. They are all free of charge. And on to the main man here today, Mr. David Whitmore, the President and Chief Innovation Officer of Vector Corrosion Technologies, and consequently my boss. He's also a registered professional engineer, a NACE cathodic protection specialist, and he serves on a number of repair, corrosion, sustainability, and education committees for ACI, ICRI, and NACE, which is now called AMP. Dave, are you ready to take it away here really soon? You've joined us before for some past webinars in our bridge preservation series, and as I joked before, if we have you back any more frequently, we'll have to call it Whitmore Wednesdays. If you're ready to go, I'll just end by saying we like to pepper Dave with questions. So if you have any good questions for him today, please submit them in the Q&A function on the top right-hand side of your screen. The best question asked today will be awarded a gift certificate from Amazon, and the best question is deemed by Dave Whitmore himself. So take it away, Dave.
Thank you, Scott. And I just need to get this. Oops. There we go. Thank you for the opportunity to present at this webinar today. Good afternoon. Good morning, good evening to everyone that's joined, depending where you're calling in from. Today, our webinar is about design considerations for galvanic anodes, or at least an introduction to design considerations and issues when you're designing with galvanic anodes. We really want to cover, I would like to cover 4 main points in this 1-hour webinar. First is just a quick overview in terms of what are galvanic anodes and why are they used. That's helped set the stage. The main 2 parts are going to be talking about design considerations and anode selection and spacing and how we get to those recommendations. We will talk about the subpoints here in more detail as we go through the sections. And relatively near the end, I want to talk a little bit about specifications, and I think if I look into the future, I see this industry moving more towards performance-based specifications than is the case today, and I think that's going to be a good thing for all parties involved. So, what is a galvanic anode? Galvanic anode is as the name intends, something that is used to corrode galvanically relative to something else. If I turn on my pointer here, you will see that this is a cutaway of just a typical discrete galvanic anode. It has a zinc core. That's the part that's going to corrode, and by corroding, give off electrons. The zinc core needs to be electrically connected to the reinforcing steel by some form of electrical connector. That's what the wires are used for in this particular case. And that zinc core is embedded within a cementitious matrix, which maintains an environment around the zinc so that the zinc not only corrodes initially when you put it in the concrete, but it continues to corrode over time thereby providing corrosion protection to the steel over an extended period of time. When we're doing repairs, you know, in a perfectly ideal world, we would like the repair material and the repair itself to be fully compatible with the substrate concrete that we're repairing. And in terms of compatibility, we want to look at all aspects of compatibility. You know, we want to make sure that the repair doesn't shrink and have cracks in it or debond from the surrounding substrate concrete. We want the modulus of the repair material to be similar to the concrete itself, so that when you load and unload the structure, the load is carried just uniformly through the section and not just concentrated in one section or the other. We want to make sure that the repair and the substrate are thermally compatible, so that when the structure warms up or cools down, all of it moves together and there's not one part wanting to expand or contract faster than the other. And from an electrochemical point of view or a corrosion point of view, we want to make sure that the repair and the surrounding concrete are electrochemically compatible, or to do something to address it. And this one, the electrochemical compatibility, is probably the most difficult one to achieve. If we're doing a repair in a chloride contaminated section of concrete, as illustrated here, we'll have some type of generally chloride free repair inserted within part of a structure, and probably there's still some chloride contaminated or carbonated concrete that is remaining. And you're inevitably going to have a difference in the environment between the steel that's in the chloride free section of concrete and the steel that remains in the chloride contaminated section. And often you're going to see that corrosion will continue, and it may even increase at the adjacent areas here as a result of this difference that exists. And that the reason it continues and tends to concentrate at those locations is because after the repair is completed, there's often a potential difference between, you know, the repair without chlorides, which will tend to have a more positive corrosion potential as compared to the surrounding area where you chloride contaminated concrete remains. The corrosion potential is generally more negative. And when you couple two different potentials together, the more negative one is what's going to corrode, and therefore that's why you see corrosion here. And many of you will have seen this in the field. On the left is an example from a marine bridge. On the right is a bridge in a northern de-icing climate. In both cases, you can see that repairs have been completed, and areas adjacent to the repairs have continued to corrode, or maybe have corroded worse as a result of the repair. But in either case, there's a delamination that's been marked out here adjacent to the repair, and you can see on the bridge deck a number of delaminated areas that are marked out adjacent to where previous repairs were completed in the past. So if we look at the most simple form of galvanic protection, where we're using localized galvanic protection, we put a galvanic anode into a repair, electrically connected to the steel, and this provides protection because the anode itself is more electronegative or more electronegative than the steel within the repair and the steel in the surrounding concrete. So within the local area where this anode is installed, current is going to flow from the anode to the steel, and corrosion of the steel is mitigated or reduced because the anode itself is corroding in its place. A couple of examples. Here you can see galvanic anodes installed along the edge of a repair where obviously chloride contaminated concrete still remains here. This slide, you can see repairs done on a marine bridge where you've got galvanic anodes to provide localized corrosion protection in the vicinity of this repair. And on the right, you see this is a bridge in the UK where they're doing concrete repairs, and galvanic anodes are installed along the interface between the where the new concrete is going to be and where the existing chloride contaminated concrete is remaining. And we're going to talk about how to design and what size of anodes and spacing and whatever that would be appropriate in different situations in a bit. One other application for galvanic anodes that you may not think of naturally is where you have interfaces between new and existing concrete structures. On the left, we have an example with a retaining wall, and a new section with chloride-free concrete's been added to a section of retaining wall that was chloride contaminated prior to the new section being cast there. And you can see that corrosion has occurred along the interface and in the old section, which you would kind of expect. To prevent that kind of problem, the bridge on the right-hand photograph here, this is a marine bridge. They are widening the bridge and adding a lane on the side of the bridge, and they have this interface between the old concrete that's 20 to 30 years old and partially chloride contaminated, and what will be the new concrete. And to mitigate this local corrosion effect that's likely to occur along the interface, they're simply putting in a line of anodes close to the edge. Okay, the other type of galvanic systems that are out there are distributed galvanic systems, and these are more generally used for cathodic protection type applications. In these applications, distributed systems are installed covering the entirety of the structure or entire sections of the structure. And the intent here is generally not just to protect a localized area where you have a localized incompatibility, like in a patch repair situation, but to protect the whole section and all of the steel kind of within that footprint. And the design for this is going to be a little bit different. You have to look at all of the steel, and you have to look at generally a higher level of current in order to provide that protection. But you know, it can be done on horizontal surfaces like this deck application, where the galvanic anodes are laid out more as a blanket and then cast into a concrete overlay, or in vertical applications where the DOT has determined that the bottom 8 or 10 feet of this abutment are sufficiently chloride contaminated that they are removing the concrete, and they want complete protection through this whole area. So we have both localized applications, and we have distributed potential applications that you might consider. Okay, so with that background, I think we want to get into talking a little bit about anode selection and spacing and different factors that should be considered when you go through this process. Back in 1999, when galvanic anodes were introduced into the market for localized protection in concrete repairs, there was one size of anode. There was only one product, and 20 years later, there's multiple sizes of anodes. We have improved the activating mortar surrounding the anodes. We've improved the zinc cores so that you have higher performance, higher current output capabilities, but there's more options available than there were 20 odd years ago. And if you go and take a look at the data sheets, you're going to see that there's a range of anodes available. They obviously have different dimensions, and they have different zinc mass or zinc content within the anodes. But in addition to these factors, there's also differences in zinc surface area, and all of these things play together to give you different options when you're doing design. So what kind of factors influence what you want to do? Probably the three main things you need to look at are listed here. The surface area of steel to be protected, number one. How corrosive is the environment or the existing structure, the condition of the steel within the existing structure, and that's going to be dependent on a number of subpoints that we'll get into. And what level of corrosion protection is desired. Okay, there's actually a lot of subpoints under these three main points, but we'll keep coming back to these three main points here, and hopefully it'll be clear as we go along. The first thing is you have to take a look at how much steel surface area do you want to protect, okay? And if you're doing a design from the fundamentals, you can take a look at your structure or the portion of the structure that you're looking at, and you can calculate the steel surface area of that element, and you can do a design all the way back to kind of fundamentals. To make things simpler, and particularly where you have fairly simple or basic geometries, we tend to normalize the steel surface area by calculating what we call a steel density ratio, which is the surface area of steel per surface area of concrete. So it's kind of like if you're standing on a concrete deck and you're looking down and you imagine a footprint around your feet, and you're looking at what amount of steel is within that concrete footprint that you see on the surface. And if you're in the US, you're more likely to do this calculation based on, say, 1 square foot of concrete surface area. If you're in Europe or another location that's using the metric system, you're more likely to look at it and say, I'm going to use 1 square meter of concrete surface area as my unit concrete area, and then you'll calculate the total steel surface area within the footprint. And as long as you use units that are consistent and they cancel out, then this calculation works regardless whether you do it in square feet or square meters, or whether you do it in square inches or square millimeters. The calculation will work. You just have to be consistent with your units. And if you end up with this normalized value, steel density ratio, then it allows you to go and look at spacings in tables much easier than if you calculate a total surface area, and then every application, every job is going to be different because you're going to have a different number of square feet or square meters of steel surface area in every job you're going to look at. So, not to take up all of the time of the webinar in running you through calculations, but just so you understand that we have a couple of worksheets that are available on the website to help you to calculate steel density ratios. There's one that is in English units, there's another one that is in metric units, and I picked one of the examples from those worksheets. On the left-hand side, I have the English example. On the right-hand side, I have the metric example. And this is, a heavily, or I would say significantly reinforced concrete slab, such as a bridge deck, where in English units, you might have number 5 rebars at 8 inches on center in both directions, and you've got 2 mats of steel. In metric equivalent, you're going to have 15 M bars at maybe 200 millimeters on center, and again in both directions, and you've got 2 mats. And you're going to calculate the surface area of, so at first when you take a look, you're going to look at, say, the top mat of bars, and you're going to look at it in the, say, the longitudinal direction, and you're going to calculate the number of bars and the total surface area of those bars within the either 1 square foot or the 1 square meter of surface area that you're working with. And you're going to come out with a number, so many square inches out of 1 square foot and 144 square inches, or you're going to come up with so many square millimeters or square meters per square meter of concrete surface area. And that will be the steel density ratio for the longitudinal bars in the top mat on that particular application. You're then going to look at the transverse bars in the top mat. You're going to calculate that, and because I've made a very simple example here with the same size bars at the same spacing going in both directions, that number is the same. And then you're going to look at the bottom mat, and again, because it's the same numbers, it's the same and the same, and you're going to add these 4 up to get the total amount of steel. It's going to come out to 0.98, and you're going to round it off, You can use 0.98 if you want, but for all practical purposes, that's going to be around 1. So first thing is to figure out the total steel area, or in this case, in a simplified version, the steel density ratio. And the second thing that we need to look at is what kind of current density do we need to provide to the steel in order to provide protection. If we look at the European standard, EN 12696, for cathodic prevention, as it's called in Europe, or in North America, we tend to call this corrosion prevention. That's the current density necessary to prevent corrosion from initiating. They give a range, they say it's between 0.2 and 2 milliamps per square meter of steel surface area. And that's useful because it at least gives you a range, but it's not that useful because there's an order of magnitude difference between 0.2 and 2. And, you know, should you pick 0.2 or should you pick 2 or somewhere in between? And that's where the first kind of decision that you're going to have to make, or that we will help you make if you go through the design process in our, at least that we use in the datasheet. So based on projects, we have found that a current density of around 0.4 milliamps per square meter was sufficient to maintain steel from corrosion initiation when you had moderate chloride levels, but that when the current dropped down below, you know, to around 0.2, the lower end of this range, you know, corrosion did initiate again. If we have higher chloride concentration, like around 1.5%, there's research out there that shows that the current density needs to be between 0.4 and 0.8. And similarly, if the chloride content is up around 3%, you're going to need a current density of around 1.6, 1.7. So we have those different current densities, and we have correlated them to the kind of the corrosion risk categories that are laid out in BRE Digest 444. They tend to kind of overlap pretty well. And so we have defined a low to moderate corrosion risk as basically 0 to 0.8% chlorides by weight of cement or carbonated concrete. High risk areas as being 0.8 to 1.5% chlorides, and extremely high risk as being 1.5 to 2.5 or maybe to 0.3% chlorides. If you consolidate everything I've said in the last 3 slides into one slide, you will come to categorization. You know, if you've got low to moderate chlorides or low to moderate corrosion risk, i.e. chloride level less than 0.8% or carbonated concrete, then we are recommending a minimum current density of 0.4 milliamps per square meter. And we're recommending that that current density is provided through the entire design life, which for the anodes in the tables, the simplified tables, is based on or assumed to be 20 years. And if we have high corrosion risk area with higher chlorides, we're suggesting current density 0.8 milliamps per square meter. And if you've got extremely high corrosion risk or higher chlorides, you know, 1.6 milliamps per square meter. So if you look at your job, you either do some pre-testing or you know based on previous experience what kind of chloride level you have, then you can go to the appropriate category, and there are separate tables for each one of these categories. I happen to pick, just for the example right now, the middle category, the high corrosion risk example. And this is one of the spacing charts from the data sheet. Our high corrosion risk, you know, 0.8 to 1.5% chlorides. You'll see on the left side here, we've got steel densities going from very low to very high. If we go back to what we calculated with our heavily reinforced concrete deck with a steel density of around 1, puts you in this category here. And if we go across to the right, we can see that for steel density 1 with a high corrosion risk, such as chloride content of say 1.2% chlorides, that the recommended spacing for XPT or XP compact anodes would be 8 inches on center or 200 millimeters. Alternatively, you could use XP2 anodes at 13 inches on center or 325 millimeters, or you could use XP4 or XPX anodes at 17 inches on center or 425 millimeters on center. It doesn't matter which of these options you pick, they're all going to provide equivalent protection, and that's going to come down to what your preference is or the contractor's preference in terms of what they want or how they want to install on the job, or maybe what the rebar spacing is and what kind of matches with that. Now, these tables that are in the data sheet are simplifications of calculated curves that have been calculated for each of these scenarios. So we were looking at the high risk table from the data sheet. The high risk table from the data sheet is are certain points taken off of these curves that are continuous curves that have been calculated. And so, for example, what we were just looking at, which had a steel density of 0.9 to 1.2, what's shown in the spacing chart in the tables is assuming the highest steel density in that range, so 1.2. And if you go up on the table, that's going to give you the 420 millimeter spacing that was shown for XP4s as an example. And similarly, the same thing exists for the low to moderate risk and the extremely high corrosion risk examples. Now, there are a number of assumptions that are built into the spacing charts and the calculations for those curves that I just showed you. And I'm going to go through and talk about some of those as we proceed here. So first of all, I guess if you look at the red X's in this diagram up here and the little note down here. So one of the assumptions that's built into the spacing chart is that the desired design current density, whether it's 0.4 or 0.8 or 1.6 milliamps per square meter, is calculated as the current density at the reinforcing steel halfway between the anodes and 4 inches or 100 millimeters outside of the repair. So anode here, or maybe look here is better. Anode here and anode here with the spacing between the anodes, halfway between the anode and 4 inches outside of the repair. That's where your design current density is calculated for. If you want something other than that, contact us. We can help you, but the tables are based on and assume that. The tables also assume that the concrete resistivity of the parent concrete is 20,000 ohm centimeter, which is pretty typical of moderately chloride contaminated concrete. And the assumptions in the tables are that the resistivity of the repair material is 50,000 ohm centimeter, which is the highest allowable resistivity based on our recommendations, or at least that's what the tables are based on. Again, if you've got different values, then they can be adjusted. The next thing that I want to just touch on is that current output from galvanic anodes is going to change over time. And generally speaking, current output is going to go down over time. It's going to diminish with time. And there's a lot of reasons for this. Obviously, as the anode corrodes, it gets physically smaller in size, so the surface area decreases. But also, as it's corroding, you're building up corrosion products that are building up resistance in the circuit. But in either case, the current is going to go down with time, and it'll follow kind of a diminishing curve like this. And if you're in a uniform environment that's not changing, like an interior application, it's going to be a fairly smooth kind of curve like this. If you look at an outdoor project like a bridge, for example, or some other thing that's exposed to the weather, you're going to tend to see the orange line here is showing the temperature, so summer, winter, and the blue line is showing current, high in the summer, down, high, down. But if you look at the general trend of the current, it's going to still follow the same kind of curve that you see here. It's just you're going to have a lot of excursions because of changes in temperature, rainstorms, etc. in the real world. Now, it's complicated to determine things when you have all these curved lines and diminishing things that you don't really understand. So basically, we've done some analysis on how the anodes have been behaving in lots of different applications. And if you plot the current versus time, but instead of on a linear scale, you plot it on a log scale, you'll tend to have either a straight line or a very close to straight line behavior. And that's because the reduction that you're seeing in current over time is an exponential reduction. And so when you plot it on a log curve, it basically tends to come out to be a straight line like this. And the slope of that line is important because that gives you an indication of how fast the current is dropping off with time. And so based on actual data from field sites and other monitored locations, for the typical anodes that are being used, we see what we call an aging term that is somewhere around 13. What that means is in 13 years, the current is going to drop to be 50% of what it was initially. And in another 13 years after that, it's going to drop another 50% from that intermediate location. And you can take that and you can plot it. And because it's a straight line and you understand the behavior, you can predict the performance a lot better. So if you have an example where, for example, you want to have 0.4 milliamps per square meter at 30 years in the future, then you can work your way back and you can determine that you need to start with an initial current density of 2 milliamps per square meter, such that by the time you get to 30, you're at 0.4 milliamps per square meter, if that's what your design requirements are. And we're using that in the background of these calculations or these tables that you see. Other assumptions that are in the standard spacing charts, the standard assumption is that it's a 20-year anode design life. The tables assume that the anode aging term is 12.5 years, so it's slightly more conservative than the 13 that I just showed there. And that's the time for it to drop by 50%. The minimum current that's being used, I showed already, but that's basically depending on the corrosion risk, either 0.4, 0.8, or 1.6. And we are assuming an average annual temperature of 50 to 60 degrees Fahrenheit, which 10 to 15 degrees Celsius, which sounds cold maybe for some people, but it's actually much warmer than it is in Winnipeg here where I live. But we'll talk about this in a minute in terms of why that's something you should think about, and you may want to adjust your designs in certain applications or certain environments. And as I've said already, custom designs can be made if you deem it appropriate. So not all anodes necessarily behave the same over time. Aging factor may be different. It could be longer, could be shorter. That is relevant because just depending on the situation, if you are wanting to have a design current of, let's say, 0.4 milliamps at some point in the future, like I just showed in 2 slides ago, then this aging term with this type of anodes and starting at this point will get you there. If you only want it to last, say, 5 years or thereabouts, you can start with this anode with a shorter aging term and still achieve that. If you want to achieve this criteria with this anode, but you want to have 10 or 20 or whatever years, then you're just going to either have to add more anodes or basically start at a higher point so that you're crossing over your minimum requirement at the appropriate location. In terms of anode current and zinc consumption, I mean, your current is going to follow a trend line like this, which you've already seen. Zinc consumption is going to follow the opposite curve. You can calculate in your designs, you know, if you know the environment you're starting off, you probably can estimate what the initial current is going to be. You know what your aging term is, you know what the current's going to be at the end of, say, 20 years in this example. And you hopefully have some data so you know what efficiency you're getting from your anodes, and you can calculate the amount of zinc that's consumed and make sure that that is less than obviously the amount of zinc that you have available to you. Couple of other things to keep in mind. One is the resistivity of the repair material. I mentioned that 50,000 ohm centimeters is our maximum. Normally that's not a problem, but if you have high silica fume or significant polymer in the mix, you are likely to be higher than that, in which case you may want to use an embedding mortar. The picture on the left shows a silica fume shotcrete being applied in a parking garage repairs with anodes. And in that case, you can see here that they have taken embedding mortar to form a conductive bridge between the anode and the parent concrete, so the anode doesn't become effectively isolated within a high resistance repair material. If you're going to use rebar coatings or bonding agents on the concrete, you can do either of those things. Just have to be careful and make sure that you're not defeating what you're trying to achieve. Personally, I think there's most places you don't need a bonding agent, but if you feel you need one, then just make sure that you're not messing up the ability of the anodes to perform. For sure, you don't want to coat the anode, and you don't want to coat where the anode is connecting to the steel. Here's an example, you know, for rebar coatings. Technically, this is a really good, there's benefits in doing this in terms of forcing more of the current to go to the surrounding area. It does take some time and labor to do it, but as I said, there are some benefits to it. Just make sure that where your connections are, you're connecting straight to the steel. And obviously you want to check that just like you would for any other connections. Okay, the last main issue that I want to bring up and talk about, and then we'll show you some other examples, is the effect of temperature. So anode current output is going to go up when temperature goes up. It's going to go down when temperature goes down. You can see that from some of the data that I showed already. If you plot the log of current versus 1 over the temperature, you're going to end up with a nice straight line like this that you can use for design purposes. And just to keep it fairly simple, you know, current is going to double every 10 to 15 degrees or every 18 to 27 degrees Fahrenheit. And that has implications, okay? I just said this already. Corrosion rate of the steel also increases as temperature goes up. So the fact that the anode current is going up and the steel corrosion rate is going up, that tends to work in parallel, so that's good. If your average temperature is below 15 or some margin above 15, there's more than enough zinc there to provide protection for 20 years. If your average temperatures are higher than 15 degrees Celsius, particularly if they're over 20 or over 70 degrees Fahrenheit, you're going to be into a situation where you may want to look at having additional zinc mass because the zinc anodes may be consumed prior to 20 years in some of those situations. And we do have higher zinc content anodes available if desired. You know, GalShield XPX is an example of that. This is essentially similar performance anode as GalShield XP4, but with twice as much zinc the same surface area, so same performance characteristics, but twice as much zinc, and specifically intended for use in high temperature and high corrosion applications. And where might they be? Well, anywhere on the globe that is in red is probably where you should be thinking about either using something like XPX, or at least being aware that your anodes will be consumed more quickly. The regular anodes are going to work perfectly fine. It's just that the zinc is going to be consumed more quickly and they may not last 20 years. So if you only want 10 years, you probably don't need to do anything. But if you want 20 years, or certainly if you want more than that, and you're any place where, definitely where your temperature is above 20 degrees Celsius, or, you know, around 70 degrees, 68, 70 degrees Fahrenheit, and that's average temperature for the year. That's not the peak temperature in the summertime. You know, you're going to want to do that. So back to this spacing chart that you saw before. I've shown this to you before, where we looked at our steel density and we said, okay, we have steel density 1. We were in a high corrosion risk environment, you know, with the chloride between 0.8 and 1.5. And we said we could use any of these things. If you've got a high temperature, or maybe a high temperature and wet marine environment, you probably would want to use XPX anodes at this spacing, just to make sure that you get the intended 20-year service life, if that's what you want. Again, if you don't necessarily need the 20 years, then you could use any of these other options as well. Okay, the tables are helpful and they make it very easy to do designs, but there are assumptions that are built into the tables, and I would say in most cases they're probably fine, but if you want to change them for some reason, customized designs are possible, and you can adjust the input factors to either be more conservative or less conservative depending on what your project situation is. You know, for example, you know, if you want to do a design based on 0.6 milliamps per square meter instead of the 0.4 milliamps per square meter that's assumed in the table, let us know. We can help you do it. You won't be able to do that directly from the tables, but you can certainly do it if you have sufficient information. Similarly, if you want to change the anode service life, and 10 years is sufficient instead of 20, which is assumed in the tables, you can open up some parameters that way. You know, if you want to change the aging factor for some reason to be more conservative, for example, you want to change to 10. If you want to change the temperature, you know, because this job's in a hot, humid, high chloride environment, you know, you can do those things. And if you have particularly if you have a big project, or you've got something that's very unique, maybe where you haven't done something similar before, it may be worthwhile to install some type of a pilot installation and collect some data from it that you can then use for a more robust design for, let's say, the main part of the project, which is maybe to come up in the future. That option also exists if you wish to do it. Okay, so just a couple of words with regard to specifications. Currently, many, and I would say most specifications that I see are prescriptive. They're very often focused on zinc mass. They mention some other factors as well, but very often they're prescriptive and they're focused on zinc mass. And although zinc mass is important, it's not the only factor that's important, and zinc mass by itself is not predictive of performance. So, you know, current output over time is really what you're looking for. Obviously, other factors like the design, chemistry, the environment, how it's connected to the steel, type of etc. All of these things affect the performance and ultimately affect the aging factor. So I think as an industry, and we see this happening in other parts of our industry, we're moving more towards performance-based designs, performance-based specifications. And I think that we will see in the future more use of performance-based specification language. It may be something like this, or it could be something different depending on what is applicable for your job. You are definitely going to want to say in your performance-based design, what current density, what minimum current density you want or expect or need to have, and depending on the corrosion risk, that number is going to be different. You are going to want to define what is the specified design life for the repair or for the anode system to be installed. If you're doing designs consistent with ACI 562, the concrete repair code, this is going to be a requirement to define the design service life. And I think someone is going to want to ensure that the information that they're getting is been verified or proven in the field in some way. So whether that's the contractor, the engineer, the owner, someone is going to want to say, okay, you say it's going to last this way, you say it's going to behave this way, show me something similar where it has, and to verify that your design is appropriate. So I do think that we will move more towards performance-based specifications as we go forward. So we have talked mostly about localized protection. I showed you a couple of pictures early on. I want to come back and just talk a little bit about distributed corrosion protection kind of at the end. For distributed corrosion protection systems, normally we're designing for cathodic protection levels as opposed to corrosion prevention or cathodic prevention levels of protection. But the same principles and the same approach apply and should be followed. We need to provide sufficient current, in this case, to polarize the steel as opposed to a specific current density. We need to consider the corrosivity of the environment and adjust the design current density accordingly. We need to define the design service life, again, to be consistent with ACI 562 repair code. And we need to consider the behavior of the anodes over time to make sure that we are meeting these requirements, the service life requirement and the need to polarize the steel over that time frame. If we're in a hot, very corrosive environment, we need to take that into account as well. And similar to the discrete anodes, it's not just a question of zinc mass. You definitely need the zinc mass to have the calculated current over the calculated time, but you need to make sure that that zinc mass is activated and is actually available and corroding when you need it. I'm going to just show you two examples here, one of which is an Ohio DOT project with a severely deteriorated concrete abutment. The DOT came up with a design where they removed the deteriorated concrete and they overbuilt the face of the abutment with 6 inches of self-consolidating concrete. Within that section, you've got distributed galvanic anodes and a new layer of reinforcing steel. This next picture shows on the left a picture taken during construction. The anodes in this case are the red strips. You can see the new reinforcing, and in the background over here on the left, you can see half of the abutment has been poured. And they wanted to do the job this way so they could keep the bridge in service and traffic up on top here while the work was going on. Forms were installed, self-consolidating concrete was pumped, and this and a number of other locations they did back at this time were monitored by connecting the anodes to a monitoring station. The monitoring that they did monitored the current output over time, which is the blue line that you see here. It's just slowly diminishing with time. and they're monitoring the concrete temperature by a thermocouple that's embedded in the concrete. So you can see summer and winter happening. This job was done in 2005, and this is the first approximately 10 years of data. One of the parameters that you are going to measure when you're doing cathodic protection design is you're going to measure a parameter called polarization. We can talk about that more in maybe a subsequent webinar. This project has met the NACE cathodic protection criteria, or the NACE standard, since 2005, and it meets that standard because the polarization has been 100 millivolts or greater since it was installed, and that's one of the criteria that is in the NACE cathodic protection standard for cathodic protection. And by documenting and logging the current output over time, we can also estimate the remaining service life. And in this case, you know, a total service life is approximately estimated to be 35 years based on how fast the zinc is being consumed. The final example that I want to show you is a project that the first phase of it was done during COVID, and the second phase is getting ready to start right now. This is a section of elevated expressway through downtown Toronto. It's in very poor condition. The substructure, as you can see, has lots of issues and deterioration. They are doing accelerated bridge replacement. So they're basically removing and replacing sections of the bridge deck at night and keeping the bridge fully open for traffic during the day. And in order to do the project this way and keep it open for traffic, they cannot remove and replace the substructure. So what they're doing is they're removing the concrete cover down to the reinforcing steel where it's not already removed, as you can see here. And they are forming and pouring a concrete jacket around essentially the concrete core that's there. Within that new concrete section, they have distributed galvanic anodes installed, and they're forming and pouring the concrete section to slightly larger than the original section was for the columns, as well as for the pier caps. Here's a close-up picture showing after the concrete removal. You can see the galvanic anodes installed here. They're the horizontal lines with the greenish color on them. They've got a layer of galvanized welded wire mesh there for crack control, and they're forming and pouring self-consolidating concrete. You can see the section of the pier cap here has been poured, and this section here is in the process of being formed. Forms will be put up on the side, and then this section will be cast back. Basically, they started at one end of the section, and they were doing the columns first, and then they were coming along behind and they're doing the pier cap. So this is near the end of that phase of the project, and you see all of the columns in the distance here are done, and all of the pier caps are done, with the exception of the one in the foreground where the columns are done, but they haven't done the work on the pier cap yet. So they did it as a phase thing, started at one end, worked the way through, and similarly they're doing the deck replacement in a similar way. So just to wrap up, a couple of points I'd just like to conclude. First is that galvanic anodes can be designed to provide galvanic corrosion prevention, or in Europe, as you'd say, cathodic prevention. They can also be used and designed to provide galvanic cathodic protection. You just need to design the system to meet the requirements of whatever you're going to design it for. The design is a very important step to make sure that you are getting long-term corrosion protection that presumably you desire. The design needs to consider a bunch of different factors. We've talked about these and some others, but we definitely need to think about the total amount of steel to be protected. We need to think about the corrosivity of the environment. We need to think about the temperature, and we definitely need to think about the anode output behavior over time, because we have to look at this design not as the design in the moment when the job is done, but we need to think about this design being functional for the design service life that is desired. And we also need to think that, well, I guess I've kind of said this here, that the service life must be defined so that the design can provide corrosion protection through the entire period. And just to reiterate what I said back before this last section, I really believe that performance-based specifications are recommended, and the more we move in that direction, the better our industry is going to be. So with that, I'd like to say thank you very much for your time and attention, and I think we've got time for a few questions. Thank you.
And thanks, Dave. And questions we do have. I've been run off my feet dealing with all the questions. I lost count at about 50. So I'm gonna have to pick and choose here. We only have a few minutes left. I'll start off with one of the first questions from David Galarza. He's asking, what is the anticipated lifespan of the anode core? I believe he's probably referring to the original XPs that you showed.
Okay, so the lifespan of the anode core is going to depend on the environment that you put it into and effectively how fast it's being consumed. So if you're following kind of the design tables that I mentioned there, the default assumption in those tables is going to be a 20-year service life. You can design for shorter or for longer than that. Obviously, you have to adjust the information that's in the tables if you wish to do that. But I would say for localized repairs, 20 years seems to be sufficient. In some cases, less may be also adequate. For distributed galvanic systems, distributed galvanic cathodic protection systems in particular, very often they're looking for that time frame or longer. 20, 25, 30 years is not uncommon. I know we did a design for a New York State DOT job where they required 50-year design. You can design for whatever the requirements are within reason, obviously, but obviously that means you need to change, the number and size of anodes in order to achieve it. So, yeah, you just have to design to achieve whatever it is your design parameters are. Okay,
and so the standard design tables, though, for those XPs are 20 years, correct?
Correct.
Awesome. A question from Andy, interesting one. Any experience or design considerations with areas of high thermal shock applications? So food manufacturing, nightly wash down with 180-degree water, and cleaners in 40-degree room set point.
Yeah, that's interesting. Yeah, so industrial environments are definitely places where you can have, very high corrosion rate situations, food processing plants where they might use a lot of brine, and then also have, hot water, hot applications, paper mills, those kind of things. Thermal shock, I don't think is going to be a problem. It's certainly not going to be a problem for the anodes or for if you do concrete repairs. It's could be a problem if you're using polymer flooring or polymer coatings. Obviously when it's hot, or if it's hot all the time, then obviously you need to design based on that. If it's hot periodically, you need to take a look at what's the actual temperature of the concrete, not necessarily the surface. You could spill hot water on the surface of the concrete, but unless you keep it on there for a period of time, the temperature of the steel is probably, or the temperature of the anodes inside there, neither of those is probably going to change very much. But if you are in let's say a stock tank in a paper mill where the operating temperature is 150 degrees Fahrenheit, then you would definitely want to take that, because that's going to be a sustained elevated temperature like that. If you're simply someplace where you could have hot water spilt on the floor, you could do some testing, but I suspect that in most cases, the thermal mass of the floor would prevent much increase to the actual concrete temperature. And if you're in the refrigerator example, I think at the very end of that question, that's a cold temperature environment. And so, the opposite of what happens when it's hot is going to happen when it's cold, and that is things aren't going to corrode as quickly, so they will last longer. So at 40 or 50 degrees Fahrenheit, or 30 or 40 degrees Fahrenheit, things are going to last longer because they're not going to corrode as quickly as if they're at say 60 degrees Fahrenheit. And so I think that's a reasonable answer for that question.
Very good, very exhaustive. So we're at time, Dave, but I have one more question I can't resist asking, and I know this is from Anonymous, but they did tell me their name and I don't have it here in front of me. You'll love it because it's a history question. How would the puck anodes of the 1990s compare to current anode performance?
Oh, that's a really good question. Well, I'd say the two things, so the mortar formulation has changed from the 1990s to currently. And so that has improved the aging factor. So basically the new current anodes the current doesn't drop off as quickly as it would with the 1990s version ones. The other thing that's changed is we tend to have, for most applications, more high surface area cores than the 1990s anodes as well. And so you'll have a higher you'll have a higher current possible out of the anodes than maybe from the 1990s anodes. So I think generally there's been improvement. The design obviously is based on the current anodes that are being produced today. If you were designing based on the original anodes from before, then you would have to take into account a shorter aging term or aging factor, and you'd have to also take into account a lower initial current output from the anode as well.
Okay, thanks, Dave. I've never been part of a webinar Wednesday where we got to all the questions, so I apologize for those of you who we did not get to your questions, which is about 50 of you. So as compensation, here's Dave's contact information. Feel free to reach out to him directly. And for some of you, Dave, I've spoken to you on the chat. We'll reach out to you directly as we have your email address to address your questions and issues directly. So leave this up for a second, and that brings us to the end of today's program. Thank you, Dave, for sharing your expertise and your experience with galvanic anode design and all the considerations therein.
Thank you, Scott, and thank you to the people that asked questions. I will take a look at them and I'll respond to any of the ones that we're not able to answer live here.
Fantastic, and thank you all for joining us. We're off on hiatus for the rest of the summer, but we'll return with a marine-focused preservation series starting in September. So stay tuned for that and visit WeSaveStructures.info if you're interested in registering for those webinars. The recording and slide deck from today's presentation will be posted shortly on the WeSave Structures website in case you were not able to catch the whole thing. Thank you again for joining us, and please go out there and save some structures.